You ready? Okay, good morning everyone. First, we have lab tomorrow in room 201, multi-phase flow lab. It is already in the syllabus. We will use the same schedule as last time. There's 1 to 150 session, 2 to 250, and 3 to 250. Anyone need to move around? You remember can we use the same schedule that we use for the separator lab? No? Yes, sir. Reminder, or you need a sign up genius to fill who do what. Split into 3. Call number. We just need 3 groups. We will do that sign up sheet online. Is that better?
Yeah, sure.
Okay, I will do that sign up after the class. Like after this class, I go to my computer and do that sign up and send it in a notification. Alright, tomorrow bring safety glass. Okay, no sandal, shoe has to close, pant has to be long pant. Alright, it has to be long pant, cannot be short pant. And if possible, use everything that cover from here. Okay, if you have this, maybe it's okay, but long pants for tomorrow. And safety glass. And we will send it out. Okay, then another one we have about next week, we have field trip, okay, to the gas plant. Both Thursday and Friday, I will go on both days. You will select one of it, either Thursday or Friday. Okay, I think a couple of you already told me that you have university to go on one of the other day, so it's fine. So we try to have half the class, 32 students go to on Thursday and another 31 students go on Friday. Okay, and for the field trip, this time we need FRC. Okay, FRC, safety glass, hard hat. If you have earplug, bring earplug. Steel toe shoes. We will actually go inside the plant. The plant process a lot of natural gas. Okay. They normally ask us to put the cell phone on the table. Okay. So when we go there, you have option of put your cell phone on the table or maybe not in your pocket. Okay, not in your pocket when we go in there. This coming Thursday, we will have the release form for the field trip sent out for you to sign in the class. Okay, I realize that you have many questions about the facility class of 4222. This coming Thursday, Mr. Bullard will give the class about water flooding and he will answer those questions. Okay, the TA time today, who need TA time today, other than Joe? Who else? Okay. If it is okay, please try to meet me after class a little bit first. Alright? You want to meet Arya? Try to meet me after class a little bit first. Yes, sir. What time do we leave for the field trip, Mr. Bullard?
Well, Thursday and Friday, bus will be right out here at this stop at 12 noon, we'll leave.
Noon, we leave.
Yeah, we'll leave at noon.
Will Dr. Wilson come with us too? Wilson, will Dr. Wilson come with us? Maybe, okay.
We'll be back right about 5:30, somewhere in there.
5:30 to 6, okay.
And I'll we'll have lunch available out here in the courtyard on Thursday about 11:30, and also on Friday 11:30. So there'll be a box lunch out there you can pick up. And then we're leaving at what time?
11:30, we have food over there. All right. Any question on this? Okay. Question about homework. Homework, you can make up the data, make up the flow rate, everything, and do the discussion. It doesn't need to exactly match with your design class, but it has to be yours. Okay. It should not be the same as your teammate. Okay. And 300, 400, 500, maybe fine. I don't want to read too much, but that's okay. We do not grade it yet. We just give you 10 when you submit it and it meets 300 words. We actually grade it on 25th of April. On 25th of April, I will go through this. So tonight, submission doesn't need self-grading. It doesn't need. You don't need a self-grading. You just do that 300 words, show that you did something. Yes, sir.
The equation part, you need to put it in the Word doc and the Excel sheet, or just one or the other? Cause I already did it in Excel, but then on my paper I also put the equation in there, but it ended up making my paper like 600 words.
Put it in the Word file too. Okay. Make it look tidy. Okay. Let's get back to the business. All right. Yes. More question?
Yeah, just understand. So like for today's submission, we get full credit as long as we're submitting it.
You get full credit as long as you're submitting it, and the number of words is not less than 300. If you get less than 300, you don't get full credit.
Okay, but then for the final project, that's when we have to go through the grading criteria.
The final project, that's when I will do exactly like what I promised you. I go through this. You have your handwriting, you have picture format or something. Okay, that is 25th of April.
Oh yeah.
Last time we stopped at orifice method. Okay, we use orifice method because it gives us relatively accurate flow rate measurement for gas test. Okay, the better meter will be Coriolis flow meter, but of course Coriolis flow meter will be more expensive. Okay, for this time we will quickly go through the derivation of orifice plate equation. It starts with I don't test you on the derivation, okay? The derivation here, just so you know what is the assumption. What I can actually test you is what is the assumption using this. Okay, we start with thermodynamic law for the case of pseudo-steady state. We have equation for capital U. Capital U is, what is capital U? What is capital U? What is capital U? Colin, what is capital U over there? Entropy. Okay, next, what's your name, sir? Okay, next, what's your name, sir? Christian with a K. Okay, what is that delta U? What? You don't know? Next, please. What's your name, sir? Alex? What is that delta U? Who know this? Joe does. Okay, Joe, what is this? Okay. Internal energy, yes, this is internal energy. Delta U is internal energy. So even though I do not ask you how to derive this, I may just give you the equation and ask you what is delta U, okay? What is ds? What is this sigma thing? I give you the whole equation. Sigma thing is the term that is about surface energy. The U is, mu over here is not viscosity, but it's a chemical potential. We neglect those things, okay?
So, what's the sigma?
Sigma is terms related to surface energy, such as the surface tension. Okay, we neglect the chemical potential. Eventually, we get TdS equal to Q plus WL. WL is work due to friction. They call it lost work. Okay, we assume horizontal flow. Delta Z equal to 0. No work done by fluid. Okay. Next to show James.
No.
In what case we have work done by fluid?
Wait, what was the question?
What is the situation that we have work done by fluid?
Change in height.
Changing height? Okay. What's your name? Hunter? Another Hunter? Okay. In what case we have work done by fluid? What about work done by gas? If it is expanding, is it work done by gas or work done on gas? By gas, right? But liquid doesn't really expand. Okay, we have 63 students, so everyone come? Alright, another one. Okay, they neglect the work done by fluid, and we put everything about the friction loss, viscosity, everything absorbed into constant. The purpose of doing all this is to do the macroscopic energy balance across the orifice plate. So we know the relationship between the flow rate across the orifice plate and the pressure drop. This is the whole purpose. So we do assume horizontal flow. So if you mount the orifice plate in the vertical direction, that's going to be a little bit odd, right? Also off because we assume no elevation term. Then we have equation, we derive it. Okay, I don't really test you on that. Eventually, so what is this equation? Or this is just to show you 1 over rho dp can be integrated like that because we use 1 over rho dp in this part. Okay, 1 over rho dp and du, u that is from macroscopic energy balance. We have, why do we have u? What is that u? Small u over there, what is it? Okay, next, what's your name in the back, sir? Richard, what is that? What is that u?
Viscosity.
Oh, let's go back. What is that u? Yes, sir? This kind of question is a fair question to be in the final exam, okay? Okay, next. What is u, sir?
Liam, velocity.
Velocity of what?
Fluid.
Gas in the orifice plate, before the orifice plate, after the orifice plate, or what?
Before.
Anywhere that we want to calculate the kinetic energy, you see that W. Delta sign is before and after. We do the energy balance across the orifice plate. So your job is to know that U is the velocity of gas. Okay. M is mass of gas. Z is elevation of gas. Okay. Alright, once we do the math, the macroscopic energy balance reduced to this, we have u du. The reason that we have du or the change of velocity because the velocity actually changed. Okay. We have high moderate velocity when you go through the orbit plate, it gets faster. Okay, and it gets even fast. It gets faster at the vena contractor point, and then it decelerates and gets slower. So there's a change of velocity. That velocity term has to be in the macroscopic energy balance. Do the math. Do a little bit more math. Okay. When we go from this to that, we just change. Have some unit conversion. Okay, and rearrange it. I know that this look quite a lot, okay, and we don't go through this, but one thing that I want you to know is, what is m dot? What do you think is m dot? Mass per unit time, right? Mass per rate. What about beta? Beta is what? Beta is very important. We define here as ratio of diameter, okay? Beta is less than 1. Okay, it's the diameter number 2 divided by diameter number 1. Diameter number 2 will be the diameter of the orifice size, that diameter. Diameter number one is the diameter of the pipe. Okay. Point one is the pipe and point two is the orifice. So beta is between 0 and 1. When I show you this equation, you need to know beta is that ratio. Okay. This ratio of diameter. And eventually we get this kind of equation. M dot is a function of average density, pressure drop, area, and beta. You see that beta? So this means the pressure drop, if we know the pressure drop alone, we cannot tell the mass flow rate. We need to know what is the size. That is a beta, right? D2 over D1. Okay. This equation is not quite ready to use yet. Okay. It is not in the form that it's quite like engineering unit. So we do some kind of unit conversion. We have delta P, PSIA, right? This is how we convert from inch of water to PSIA. Okay, so how do we convert from inch of water to PSIA? What is the conversion factor? The 2.3 thing. Oh, okay, that is feet or something. But basically, we do this. Okay, we have put inch of water here. That is the conversion factor. That is the density of water, G value, and that G sub C, and that is to convert from inch to foot or something. Your job is know how to derive the coefficient. Okay, if I have delta P PSIA and I input delta H in inch of water, how do we convert it? All right. So basically, the answer would be that divided by that divided by that. Just that, and G sub P cancel each other. That is. I was told that that is freshman engineering, and I should not go too much into detail, but I can test you on that. Rearrange it into the unit that is easy to use. Okay, easy to use means not pound mass per second, but mmSCFD. Okay, then we get this is the equation before mmSCFD. Okay, it's still quite a lot. So rearrange it more. I get this. Okay, QH equal to C prime square root of HW P sub F. HW is differential pressure in inch of water defined at 60 Fahrenheit. P sub F is absolute static pressure. Okay, in PSIA. C prime is a orifice constant. Okay, that is C prime. C prime taking into account of every term. Okay, every term that is in front of it. Every term means it's already include beta. Okay, what is this CD? You see that CD? Is it the drag coefficient? Oh no, it's a C multiplied by the diameter. Okay. So we absorb everything becomes, instead of C, we use C prime. It already have square root of specific gravity, already include temperature, already include compressibility factor, diameter ratio. The term that matter a lot is beta. Okay, because when the size change, it changed completely. That's why the last lecture I showed you this number. F sub B, basic orifice factor, it go from 12 to 1,498. Okay, it changed a lot because that is the term to account for beta. Other term, sometimes it's 0.008 or 0.006, it doesn't change much. Okay, this is a Reynolds number term. And sometimes you see 1 to 0.098. So the most important one is basic orifice factor. Okay, or F sub B. You may have several things. Okay, F sub B, F sub R, blah, 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 blah. I ask you, which term can change significantly? A, that, B, C, D, E. So your answer will be A. Okay? Alright. So this C prime taking into account of all those. So this means temperatures matter, compressibility factors matter. Where do we get those numbers from? From a table that both seller and buyer agreed upon. Okay? Let's take a look at the unit. QH here is SCFH, okay? C prime, horrific constant, P sub F, PSIA. Where else do we use PSIA? Is that in compressor question? I have seen compressor question that some of you use PSIG to get a compression ratio that's straight to 0. Okay, don't do that. Use PSIA. Alright, how do we get C prime? C prime is the multiplication of each of these terms. Okay, get each of the term from the table, multiply them together, we get C prime. Then we read pressure drop. We know static pressure, then we can calculate flow rate, standard cubic foot per hour. Easy? It's just plug the number in. I tell you C prime equal to 15, that equal to that much, you multiply them together, get Q sub H. Easy, right? Is it?
So where are all the tables for all of those constants in C prime?
Not all table is given here, okay? All the table data will be in the homework and the exam as needed. Okay, the table will come from ICOCU, okay? Let's go through each variable, okay? We have f sub b. How do we read f sub b? I need to know orifice diameter in inch. I need to know, okay, let's say my orifice, the whole size maybe 1.125 inch. What about my pipe size? If my pipe size is about 3 and the actual pipe size is 2.9, it's depending on how thick is the pipe, right? Which schedule is the pipe. Then I read the number. So that will give me f sub b. Okay, good. This is just how to read the table. In the exam, I will give you two kinds of table. Flange tap and pipe tap. Table value for f sub b, they are not going to be the same. So what you just need to know is when you see the picture, this called flange tap and that called pipe tap. Just use the right table. Okay? So how can you do the test? So if it's pipe tap, use pipe tap. If it is flange tap, use flange tap. So this is flange tap, B value. So this is to calculate f sub r. F sub r is one factor of the C prime. So we need B and square root HW P sub F. Okay? B value, this is B value for Reynolds number factor. B value is from here. Okay? B value is from here. It's just read the description of the table. So F sub r is the second one. So the first one is the basic orifice factor. Second one is F sub r. F sub r is for Reynolds number. They call it Reynolds number factor dependent on part diameter, viscosity, density, velocity, gas. Okay, use this table for flange tap and pipe tap. Okay, it's just reading the table. Anything else that you want to ask other than how to read the table? How to read the table is you go back to this thing, you find out which one that we need to use to get C prime. You go to the corresponding table, read it, put that, make sure that if it is flange tap, use flange tap. Okay? Beta ratio D over D, that is the whole size over the inner diameter of the pipe size. We need to know that in order to read Y1 ratio. Okay? You will do all this in the homework. Okay, Y1 is an expansion factor. Which factor is account for what? I don't quite answer that. We basically skip. Okay, what is FPB, FT, all those things? No, I don't quite answer that. What I'm going to ask is F sub B. F sub B account for what? Size of the orifice plane. Okay, that F sub B. The rest is just open the table, read it. Okay. Okay, we skip all that. Okay, in the homework, you will get one chapter of ICOCU. This material is not going to be posted online. We just do the fair use, we just distribute in this class. You will read the example. I change some number and you redo it. Okay? They have the procedure on how they do it. You go through all that. Reading the chart. Okay. Reading the chart, we have two kind of chart. This class, I don't actually cover the square root chart, but it's easy to read. If you want to do it, you can read the procedure how to read it. This is the linear chart. Linear chart, we have two lines. Okay. One line is this line. Okay. This line doesn't have much fluctuation. Between P sub F and HW, which one should be this line? And what's your name, sir?
James,
James, what do you think?
I have no idea.
Choice A, P sub F. Choice B, HW. What is that line, James?
HW.
Okay, next. What's your name, sir? Anderson? P sub F or HW?
Piece of pressure.
Very good, correct. When you see it's like more or less constant, that is the pressure in the line. Okay, the pressure in the line, whether we have flow or not, it stays more or less the same. But the pressure drop across the orifice plate is have the fluctuation because sometimes we may not have any flow. Okay, rule of thumb to select the orifice plate. How big is the orifice plate size? Do we do just that, or we do like that big? How big should be the whole size? My answer is that whole size should allow pressure drop in inch of water about 20 to 80% of the reading. In this particular case, the reading for the pressure drop or HW in the inch of water unit is from 0 to 100. So this means okay, pressure drop will be 20 to 80 inch of water. We want the pressure drop to be between 20 and 80 inch of water, or 20 to 80% of the reading. Okay. If we have a different chart, it may have different range of the reading. So for the meter to work properly, the signal should be between 20 and 80. Okay, percent of the reading. So next question come. I know the flow rate. Okay, I already know the flow rate. My flow rate, okay, 20 million standard cubic feet per day. What is the size of the orifice plate should I select? Oh, this is not as easy as I tell you pressure drop. I tell you P sub F, HW, you open the table, get CPAM and calculate the flow rate. So this is the inverse problem, which is actually a real problem. You know the flow rate. Roughly about, okay, maybe 17 to 23 mm, okay, million standard cubic feet per day. What is the size of the orifice plate I should have to use? How do I do it? Elizabeth, is it Elizabeth? Mm-hmm. How do I select it? Okay, next, what's your name? Martin? Okay, Martin, how do you select it? A chart? A chart, there is no a chart for doing that. What I will do is this. I have to do some calculation. Okay, I assume, okay, HW is about 50 inch of water. Okay, that's HW, 50 inch of water, right at the middle of the chart. Okay, for the case between 0 to 100. Then I know the value of P sub F, which is the static pressure. I say, okay, 500 or maybe 1000 psi. Okay, then I calculate. I know the flow rate. Okay, I know C. Okay, let me go back. I put here flow rate that I know. Okay, I put here, maybe I put here P sub F that I know. I put here C value that I know. Then I calculate pressure drop. If the hole is too small, your pressure drop can be like 10,000 inch of water or 1,000 inch of water. You know that it's not right. Okay. If the hole is too big, the pressure drop may be just okay 0.001 inch of water. or 0.1 inch of water, you know that it's not right either. Okay, it has to be measurable. Okay, so this means it requires some iteration. You guess, hey, the pipe size is, okay, where do I get that value? I have the pipe size of 4 inch. Okay, how much should be my orifice plate? I may select one of them and do the calculation first on what is the pressure drop. I select another one, what is the pressure drop, and find the one that have a reasonable pressure drop. Reasonable pressure drop means 20 to 80 inch of water for the first case. It could be something else, okay, depending on the accuracy of the measurement. Okay, but this is the first step if you don't have any idea. If you have more information, for example, you know that the pressure that we will do the measurement is in a certain range, then you do this calculation and make sure that that pressure drop is not going to exceed the range that your company used. Probably is 20 to 80 inch of water. Okay? There are another kind of chart. The first one is linear. Another one is square root. Square root has another way to calculate it. Chart reading over 10 square something. We don't cover this, okay? Just so you know that, okay? Look at this thing. Once we have the chart, what do? Manually, we can integrate it. Integrate it means, okay, we know HW, P sub F, and then we put in that equation, we get the flow rate, at every ounce, and add them together, okay, to know how much it is. But right now it's all digitized. So, Mr. Bulat, can you comment on how do they do it on the old day for this integration? In the old day, do we have it manually and like 10 people do it, or how many people require to do this?
So in the old days, go back to the chart for a second. You had to read off at any given point what the HW was and the static line pressure, and calculate a volume for that time period. And then they slowly developed integrators, which the individual would sit down with that chart, place it on like a round rotary table like the old record player, and they would run a needle across the top of that chart and trace the chart, and then it would calculate the rate at each of those hour points and add them up and you get your 24-hour day rate. So you hardly see these charts anymore being used. Instead, there's a flow computer up there about the size of your iPhone. And it sits up there and it's doing that integration, taking those signals as they come across the orifice plate, integrating them in there and giving you a digital readout of that. That's electronically what's happening when you see with the mechanical signal. And the reason for the 20 to 80 range back in the old days, look at the chart as you get below 20, how close together the lines get. So if you've got to read that, you know, am I reading 10 or 12? So you get outside that 20% range, the numbers get far enough apart they're easier to integrate. You go to the 80% range, so you allow yourself some room for slugging. Gases will go through there and slug. If you hit a slug of gas, it goes off the chart, literally. You let gas pass that you haven't measured. So you want to stay on the chart, so you allow some room for it. That's where that 20 to 80 is coming in when those charts were established.
All right, thank you. How many people do we need to do this integration? Manually?
One,
Just one? Okay.
give them lots of time in there.
Okay, this part is example. You may go through this, but you will see specifically what this is about the square root chart. Okay, this is about the square root chart. We skip. Okay, selection of the orifice meter. Where there are many factors that we need to consider, such as maximum peak hourly rate. Okay, duration of maximum peak, maximum hourly rate or its uniformity. How big is that peak? Okay, metering gauge pressure required and available, Permissible pressure variation, how much is the pressure variation that we have? Okay, the working range of orifice plate and differential gauge is from maximum capacity to about 1/16 of the maximum. So that is the working range, but we try to stay between 20 and 80. Okay. You may read all this, okay, by yourself. Okay. Differential should not exceed static pressure. That's you know, right? Okay. The middle run ID should be at least 1/3 larger than the orifice opening. That's roughly how to be selected. Both differential and static pressure pen should preferably operate within the middle, 60% of reading charge, or between 20 and 80. Top 5 reasons. What are those things that make reading to be wrong? Okay. The edge. Okay, if the edge getting not sharp or dull, then it doesn't work well. Okay. Middle tube, condition of the middle tube. So coefficient are obtained from the test with the commercial iron pipe with corresponding roughness. Measurement would be high with 2 smooth pipe and low with 2 rough pipe. Why do we worry about the roughness of the pipe? Or when do we worry about the roughness of the pipe? When we have turbulent flow, right? And we have pipe tap. Pipe tap with turbulent flow, the pressure drop is dependent upon the roughness too. Flash tap, this thing we have less effect. Pulsation, if we have pulse, okay, it is difficult to do the measurement. If we have wet gas or we have some liquid phase, okay, that's make error in the measurement. Because all these calculations we assume single phase flow across the shock, not flow of gas with small droplet inside. No. Okay. And number one reason is humber change orifice plate and does not note on chart or report 21. Okay. Good. So out of those 5 reasons, you should know like 2 of them. Correct? This is a mass flow meter. Orifice meter may be used to measure the mass, and this is another equation to get the power mass per hour, okay, with different value. Alright. You may not need to care much about this because you have to be able to do it anyway. If I give you standard cubic foot per hour, can you tell me power mass per hour? Yes, pass, no, fail, okay? Try that. Use PV equal to CNRT to do the conversion. When we know standard cubic foot per day or standard cubic foot per hour, you should be able to calculate and get power per hour without any difficulty. Okay? Orifice sizing, from chart HW between 0 and 100 inch, optimum is 20 to 80 inch, we talk about that. Okay, sizing, we calculate pressure drop for each case and make sure that it's between 20 and 80% of the chart range. Just that. Any question? Can you do the orifice? What kind of orifice question on the exam that you may expect? Okay. Number 1, the factor that impact the accuracy of the orifice plate reading. Number 2, you have to be able to convert from standard cubic foot per day to pound mass per day or something. That unit conversion. Number 3, if the number is given, okay, you have to be able to use this equation. And when a contractor, you know which point is which, right? And you know which point has highest pressure. And you know this we call senior orifice fitting, A.O. Smith. Okay. What is A.O. Smith? What is the full name of the lab unit? You know those. In the derivation, it's not much of the problem. I give you this equation, I ask you, what is mu? Okay, what is W? You have to be able to answer that. What is the unit? Don't get nervous, okay, when I ask you about the unit of that, because the unit of that will be pressure multiplied by volume, or the unit pressure multiplied by volume has a unit of energy. Okay, you may say Joule, just that. All right, nothing else on this. Okay, let's move on. Pipeline for gas and liquid. Okay, here's the equation to calculate pressure drop for flow in a pipe. Okay, this equation works for both gas and liquid, but we mostly use it for